Welcome to the how-to video for the effect of nuclear charge. When we talk about effective nuclear charge, we have to think of Coulomb's law. When we're talking about Coulomb's law, we're really just thinking about the strength of an interaction between two electrical charges, such as a nucleus and an electron. In the nucleus, we have a lot of positive charges, and an electron we know is negatively charged. And so there's going to be some attraction between these positively charged protons and negatively charged electrons, which are circling the nucleus of the atom. But we have to understand Coulomb's law says that the force increases as the nuclear charge increases and will decrease as the electron moves farther from the nucleus, which really just means that if we first just think about the distance between, in the same case where we have a positive charge and a negative charge which are farther apart, this distance is greater, and so these two opposite charges can't really feel one another as easy. But we could also think about effective nuclear charge when we think about a larger charge. So instead of having a plus 1 minus 1 charge, what if we had a plus 100 charge and a minus 100 charge? Well, this attraction is going to be much, much stronger because the charge of those electrons or those protons is much, much greater. And so this really helps build what we call the effective nuclear charge, which is the charge the valence electrons feel from the nucleus. And so when we talk about effective nuclear charge, we abbreviate it with ZEFF. And we can then solve for the ZEFF, the effective nuclear charge, by taking the atomic number minus what we call the screening constant. The screening constant is just the core number of electrons, the inner valence, or the inner electrons. The valence electrons are the outermost electron shell. And so when we really think about effective nuclear charge, if we were to draw out our atoms in a simple 2D drawing, we could say, okay, well, let's actually calculate the effective nuclear charge. Well, sodium has a positive 11 in its nucleus. It has 11 protons based on its atomic number, and so we could take its atomic number minus the core electrons. The core electrons are everything inside of the valence shell. So our valence shell is this n equals 3 shell. Well, what's inside of that is the n equals 2 shell and the n equals 1 shell, and there's a total of 10 electrons in that region. And so we take 11 minus 10, which is going to leave us with a plus 1 effective nuclear charge. For magnesium, which is just 1 over from sodium, we do the same thing. Well, its atomic number is 12, so it has 12 protons in the nucleus. And in its core electrons, it has the same amount. It has 2 in the n equals 1 and 8 in the n equals 2 electron shell, which again is still going to be 10 as its core. And so now magnesium has a positive 2 effective nuclear charge. And so what this tells us right away is that the trend for effective nuclear charge is going to increase as we go from left to right on the periodic table. But what about when we go down the periodic table? Well, as we go down, we would encounter potassium. Okay, and potassium is directly underneath sodium. It has a atomic number of 19, meaning it has 19 protons in its nucleus. How many electrons are in the core electrons? Well, it's going to be 2 in the n equals 1, 8 in the n equals 2, and 8 in the n equals 3, which really means that we have a total of 18 core electrons with just 1 in its valence shell, which is in the n equals 4 electron shell. This gives us a positive 1 effective nuclear charge as well. And so what's interesting here is that we see the effective nuclear charge for sodium is plus 1, the effective nuclear charge for potassium is also plus 1, and these are in the same group of the periodic table, in group 1A. So how do we determine the effective nuclear charge? Well, if we understand the effective nuclear charge is the charge that a valence electron feels from the nucleus, and we really think about the valence electron in sodium is this one, and it's going to feel those 11 protons fairly okay. If we think about this electron in potassium, which is 1 shell farther out, but the charge on the inner nucleus is much greater. Thus, what happens is this plus 1 for potassium is actually just a little bit greater than plus 1. It feels that charge a little bit more because it has more of a positive charge and because more of these electrons are kind of spread out in the n equals 2 and n equals 3 electron shell. And so ultimately what we find is that the effective nuclear charge actually increases as we go down the periodic table. And so we can kind of summarize that here where we say the effective nuclear charge increases from left to right across any period and increases down the column of a group in the periodic table. Understanding that the strength of the effective nuclear charge is much, much greater when we talk about as we go across a period rather than down a column. And you saw that because the sodium was +1, potassium were both +1, whereas sodium was +1 and magnesium was +2. And so you get a greater effective nuclear charge increase as you move across a period. That completes how to for the effective nuclear charge.